Hello, everyone. My name is Jiaxin from Key Laboratory of Computational Optical Imaging Technology, Aerospace Information Research Institute, Chinese Academy of Sciences, and College of Resources and Environment, University of Chinese Academy of Sciences. I am going to introduce my latest work about unsupervised hyperspectral and multispectral image fusion. First, I will give a short review of my research background. And then I will introduce our work for unsupervised hyperspectral and multispectral image fusion. The availability of data captured by different sensors opens up the possibility of utilizing multi-source data sets in a joint manner to further improve the performance of applications at hand. Multi-source data fusion has received enormous attention. An illustration for multi-source remote sensing data fusion is provided here. First, multi-source remote sensing data is captured from different platforms, such as satellite, airplane, and ground station. Typical multi-source remote sensing data includes hyperspectral, multispectral, LiDAR, SAR and infrared. By designing different network structures, we can apply these data to various applications, including object detection, land use land cover classification, and so on. More information about multi-source remote sensing data fusion can be found from this paper listed below. This presentation focuses on hyperspectral and multispectral data. Here is an example from ZY1-02D satellite, where the left is multispectral data and the right is hyperspectral data. However, there is a trade-off between spatial and spectral resolution. That is to say, multispectral data have high spatial resolution, but with low spectral resolution. By contrast, hyperspectral have high spectral resolution, but with low spatial resolution. Spatial and spectral resolution are two important domains to describe our target of interest. Therefore, combining the high spatial resolution and the high spectral resolution to generate a high spatial resolution hyperspectral image is of great importance. Here, we give an example of hyperspectral and multispectral image fusion. By combing their own advantages, we can generate high-resolution hyperspectral image. This new data have both high spatial and spectral resolution, allowing for a better identification and classification. Existing paradigm for deep learning-based hyperspectral and multispectral image fusion can be divided into supervised and unsupervised. There exist several problems for supervised methods. One is that the large number of training triplets is the prerequisite of the superior performance for these data-driven methods. In reality, collecting and preparing these training data sets renders them inherently impractical. Another is that well-trained models are not suitable for other scenes or other data captured from different sensors, leading to low generalization. Considering these issues, developing unsupervised method is a new trend. Different from supervised method, unsupervised methods only need observed hyperspectral and multispectral pair for network optimization. And then, I will introduce our proposed unsupervised network for hyperspectral and multispectral image fusion. Before introduction, some notations should be given. K stands for Low Spatial Resolution Multispectral Image, Y stands for Low Spatial Resolution Hyperspectral Image, Z stands for High Spatial Resolution Multispectral Image, X stands for High Spatial Resolution Hyperspectral Image, P is matrix representing PSF blurring kernel and downsampling operator for spatial degradation, S is matrix representing spectral response function for spectral degradation. The degradation model describes the relationship between unknown X and observed Y and Z. By exploiting and exploring the degradation model, a latent relationship can be established. That is to say, the spectrally degraded Y should equal to spatially degraded Z. By observing the degradation model and the latent relationship, we can find that K and Z are spectrally degraded from Y and X via the same degradation matrix as so, if we can establish the spectral inverse mapping from K to Y, and apply this mapping to Z, we can generate the unknown X under the unsupervised framework. Based on this idea, we propose a three-step network to achieve unsupervised hyperspectral and multispectral fusion. Step 1 aims to learn unknown degradation parameters, and get 2K. In this step, depth-wise convolution is used to simulate PSF downsampling and point-wise convolution is to simulate the SRF downsampling. By minimizing the loss function, we can jointly learn the degradation parameters K1 and K2. Once obtaining K1 and K2, we can learn the spectral mapping from K to Y. In order to fully utilize the information hidden in K1 and K2, we design a fusion module to integrate K1 and K2, obtaining K. Then, using multiple 1x1 convolution operators to establish the spectral mapping. Last, we apply the learned spectral mapping to Z and obtain desired X. One publicly available HSI data named Jiaxin is selected as a benchmark for comparison. After discarding noisy and water absorption bands, a sub-image with size of 400 x 400 x 110 is cropped as a reference. Moreover, Gaussian blurring with a downsampling operator is used to generate low spatial resolution hyperspectral image, and worldview 2SRF is used to produce high spatial resolution multispectral image. 9 state-of-the-art methods are selected for comparison. Moreover, 5 quantitative metrics are adopted, including root mean square error, peak signal-to-noise ratio, spectral angle mapper, correlation coefficient, and relative dimensionless structure similarity. Table 1 shows the quantitative assessment of Jiaxin datasets. Generally, matrix-based methods are prone to spectral distortion and lead to low-quality image reconstruction. However, DL-based methods achieve more satisfactory outcomes in both spatial and spectral domains. As can be seen, our method obtains the best results in terms of all metrics, which firmly demonstrates our ability in spectral preservation and spatial enhancement. Besides, we also show the visual evaluation. Our method can effectively inject spatial details for better visual observation. To provide a more straightforward comparison, the SEM heat map is shown in the second row. It can be observed that our method has a smaller error amplitude, which directly reflects our spectral preservation ability. For more information, welcome to contact me via WeChat, GitHub, and ResearchGate. That's all. Thank you.